5.2.1, finding one-side limits. So what I would do is pause the video and do these first problems on your own, and then unpause it to check your work. So the first one we're looking at the limit as x approaches 2 for this function right here, this graph. So remember, as you're looking at this, if you don't have the plus or the minus next to it, that means you're looking at as you're approaching from the left side, which is over here, and from the right side, which would be this side, what are the y values on your graph approaching? So the y values on my graph are approaching this open circle that we have. So even though the function is defined at f of 2 as being equal to 1, we're not concerned with this point. We're concerned with what's happening on our graph. So then that tells me that at f of 2, even though it's 1, the limit is equal to this y value here, which is a y value of 3. So the next part says we want the limit, and remember when that negative sign's there, that means from the left. And we learned that the plus sign right there means from the right. So the limit as x approaches 2 from the left side is again still 3, and from the right side is still 3. And that's why the double-sided limit exists, because remember, if the limit is not approaching the same number from the left and the right, you can't write the two-sided limit. So looking at the next one, we have the limit as x is approaching 6 from the left side. So here is an x value of 6. Just going to draw a dotted line down there. And so remember, this is your left, this is your right. So as we're approaching 6 from the left, we see that our y values are approaching 5. From the right side, as I get closer to this value of x of being 6, my y value is now approaching, you can see that 4. And so that means that the left and the right side are approaching two different values, so the double-sided limit does not exist. So D, N, E for that. And again, that should be just review because we've talked about that already. So let's go ahead and talk about or look at our piecewise defined functions. So we're going to go ahead and graph this. So we're looking at first a linear function, and we're graphing it from values of x less than 2. So I'm going to start off at my restriction. So if I plug 2 in here, 2 times 2 is 4, minus 1 is 3. So at 2, I have 3. And it's an open circle because, again, it's less than 2, not equal to. Since this is a linear function, you can see that your slope is 2, so we're just going to go down 2 over 1 and down 2 over 1. And that makes sense because our y-intercept is negative 1, so my graph is just going to keep continuing down 2 over 1. So I'll get a ruler to graph that. So that is that first part. And for the next one, we have, it looks like it says if x equals 1, we have a horizontal line at y equals 1, but only for x values equal to 2. So in this case, that means we really just have a closed circle. I'm going to do a different color at 2, 1, which would be right here. And for the next part, it says we have starting at x values greater than 2 for x minus 2. So again, it's a linear function. And now we have values that are greater than 2. So if I plug 2 in here, 2 minus 2 is 0. So at 2, 0, we have an open circle. And my slope is 1. So we're just going to go up 1 each time. So I'll get my ruler again. And that is my piecewise defined function. So let's go ahead and look at evaluating some limits. So for the first part, it says we want the limit as x approaches 2 from the left side. So here's my x value equal to 2 would be at this line right here. So the left side is over here. This is the right side. So as we're approaching an x value of 2, our y values are approaching this value up here of, it looks like 1, 2, 3. And from the right side, if we're looking at our graph, so on the right side, of 2, my values are coming closer and closer to 0. And the double-sided limit would not exist because, again, there is a break in my graph. The left side and the right side are approaching 2 different values. Therefore, the double-sided limit does not exist. So can we do this without having to graph these functions? Yes, we can use our restrictions to help us. So let's look at this next one without actually having to use the graph. So for this next one, we want to, given, and this should say f of x, just got cut off there. So if f of x is equal to this function here, we want to find each limit if it exists. So for this first one, we're looking at 4 from the right. So you want to figure out which restriction does 4 from the right fit in. So 4 is bigger than 3, so that means we're going to use this top equation right here. So we're going to plug 4 into this top equation, and whatever it gives me is going to be my solution. So if I plug 4 in, I get negative 4 squared plus 6 times 4 minus 6, which ends up giving me 2. So that means the limit as x approaches 4 from the right is equal to 2. Well, 4 from the left is also using this restriction. So that means that, again, if we plug it into the equation, we already know from this last one that we're going to get 2, because this top one stands from the right and from the left. So now we're looking at 3, which is where our restrictions are. So here, if we have values bigger than 3, we know that's going to be to the right of 3. And here, if we have values less than 3, that would be to the left. So this one, remember with the plus sign right there, means the right. So if I'm looking at 3 from the right, I'm going to use that top equation. So I would plug in 3. So negative and then 3 squared plus 6 times 3 minus 6, which is equal to a value of 3. And now this one is looking at from the left. So that means I'm using the bottom equation. So in this case, I would have 3 minus 1, which is equal to 2. And so for this, you can see for 2, I know that, for as x approaches 3, that my function is coming to 2 different values. So the double-sided limit, if we were to graph this piecewise defined function, you would see there would be a jump in between those values, so that it would not exist. So let's go ahead and take a look at this graph here. And on this graph, we're going to evaluate these limits. So again, try to do this on your own and we'll look at it together. So the first one is looking at the limit as x is approaching 2 from the right side. So here's an x value of 2. So from the right side would be over here. So that looks like it's approaching a y value of 3. From the left side would be on this side over here. So from the left side, we are approaching a y value again of 3. The limit as x approaches 2 for the double-side limit, because the left and the right side are coming to the same value, is also equal to 3. So now let's go ahead and look at 6 from the left. So 6 from the left side would be up here, and notice your graph is coming to a y value of 7. 6 from the right side would be down at this y value over here, which is at a y value of 2. And so because the left and the right sides are coming to 2 different y values, that means the double-sided limit does not exist. And then we want to, now this is just evaluating the function at f of 2. So I'm looking at my graph for where my graph is. And in this case, notice there's an open circle here, so we can't use that value. But we do have a closed circle up here at 10, so f of 2 is actually equal to 10. Let's say that this closed circle is not there, and instead we just had the open circle, then you would say that f of 2 is just undefined. It's not part of your graph, or it's not in the domain. All right, so that's graphically looking at our functions. Let's go ahead and see if we can look at finding the limits algebraically. So looking at this first equation here, if I want to find this algebraically, well, that means I need to figure out, is 3 from the left in the domain of this? So remember, when we are finding the domain, we have to watch out for variables in the denominator, because we can't divide by 0. And the second thing we have to watch out for are variables under even roots because we can't take the square root of a negative number. So for this one, we have variables underneath the roots. Remember, we learned early in the year to algebraically find this. We want to take what's underneath our root, and we're going to set it equal to 0 and solve. So we get negative x squared equals negative 9. Divide both sides by the negative, so x squared is equal to 9. Take away that power, you need to do plus or minus the square root, so plus or minus the square root of 9, which is just equal to plus or minus 3. And so remember, in the beginning of the year, we drew our number line to look at 3 and negative 3. And because this is in my numerator, we would be equal to 0. If it was in the denominator, it would be not equal in an open circle, but we have closed circles here at 3. So we need to figure out where would our graph be. So let's do some test points. So if I do below negative 3, such as maybe let's do negative 10. So negative 10, if I plug it in here, I would get the square root of 9 minus negative 10 squared. And so negative 10 squared is 100, but notice you would have the square root of 9 minus 100, which is going to give me imaginary answers. Therefore, I know that this side is not a part of my graph. Let's do in between negative 3 and 3. 0 would be the easiest number, so the square root of 9 minus 0 squared would just give us the square root of 9, which is equal to 3, so that one's a real number answer, so that does work. So all these values in between negative 3 and 3 are part of my graph. If I do numbers above 3, such as 10 again, or even if I did 4, I would get 9 minus 16, which again is imaginary solution. So the only part of our graph that we have defined is in between negative 3 and 3. So if I'm looking at 3 from the left, so here is 3, and this is the right side of 3 and this is the left side of 3. So I would have that on as a part of my graph. So since I would have it as a part of my graph, that means that this is in the domain. And so therefore, because it's in the domain, we can go ahead and figure out what the limit as x approaches 3 is just by plugging 3 into my equation. So the limit as x approaches 3 from the left side would just be plugging that number in, so 9 minus 3 squared. And of course, 3 squared is 9, so we get the square root of 9 minus 9, which is the square root of 0, which is just equal to 0. So that means that the limit as x approaches 3 from the left would be equal to 0. And again, that's because it's in the domain, because the domain of this entire function is from negative 3 to 3. And so because it's in the domain, that is why we can actually find the limit. So even if you were still unsure, well, you can always get out your calculator to kind of confirm this. So if I go to my calculator, we're going to go ahead our y equals, and we're plugging in the square root of 9 minus x squared. And if I hit graph, you can see that this is my graph right here. So here's 3, the left side of my graph exists, and I can see that my y values are getting closer and closer to 0. I can even zoom in some to have a better look. And so if we zoom in, oops, I should change the window. Let's go ahead and look at 0 to, let's do 3.2. So we can see what's happening on our graph right over here, but you can see that your values are getting closer and closer to 0. So they're actually equal to 0 in this case because 3 from the left is in the domain. All right, so let's go ahead and look at the next part. So now this graph, or limit, sorry, is saying 3 from the right using the same one. But if we go back over here to our domain, the right side of 3 does not exist. It's not part of our graph, and we just saw that when we looked at our graph. So looking at this graphically, you can see there was nothing to the right side over there. I'm going to go back to a standard window. So since there's nothing over here, that means that 3 from the right is not in my domain. Therefore, the limit does not exist. And so that would be looking at your one-sided limit. So it's very important for the one-sided limits to always look at your domain. So let's go ahead and look at question number 7. So for this one, we have the limit as x approaches -3 from the left side. So the first thing we're going to do is look at our domain. Well, we know we have variables in our denominator here, which we can't have, so we're going to set that not equal to 0 because we can't have 0 in the denominator. So that means x cannot be equal to -3. We also have a radical that we have to worry about here, which means we can't have negatives underneath our radical. So it's in my numerator, so we are allowed to set that equal to 0. So we get x plus 3 equals 0. So in this case, x is equal to -3, but over here we said it can't be equal to -3 because it makes my denominator 0. So that means we are always going to use the one that it can't be in this case. So we would have an open circle there on our number line if we draw out to find our domain. So here we have 3, or excuse me, -3. It's an open circle because of our denominator right here makes it 0, which we can't have. And then I want to figure out which way I'm highlighting my line. So if I pick a number below -3, such as maybe -10, if I plug -10, it doesn't make my denominator 0 here, but -10 plus 3 gives me -7 underneath this radical. So I know that these numbers over here to the left of -3 will not work. Let's try the right. So something to the right that's easy would be 0. If I plug 0 in here, we get 0 plus 3 over 0 plus 3. So 3 over 3 is 1. And in here, if I plug in 0, I get 0 plus 3. The square root of 3, again, is a real number, so that's okay. And then plus 1. So this side does give me real number answers. Therefore, it is a part of my domain. So my domain is from -3 to infinity, not including -3. So because we're looking at -3 from the left, we want to see, okay, well, here's the left side of -3 and here's the right side. Well, I can already tell you right now that that is not in the domain because there is no part of my graph over here. They don't work because they fail when we plug the numbers in. So that means this does not exist for the limit. So over here, now we're looking at the same equation, except for we're looking from the right. And if we go back to our domain over here, you notice that the right side of my graph does exist. So that means if I want to figure out what the domain is, I want to look at plugging these values in. And we can use our calculator to help us for now. So if I look at my calculator, y equals, we're going to go ahead and plug this in. So we have the absolute value of x plus 3 divided by x plus 3. Don't forget to use your parentheses. Plus the square root of x plus 3, and then plus 1. So let's go ahead and take a look at the graph. So here's what my graph looks like, and you can see that the left side of this graph doesn't exist. So we're concerned with what that value is right there. So let's actually see what happens when we plug in -3. So if I plug in -3, you can see nothing is going to come up on my graph because, again, it's not in our domain. But remember, the limit is as we're approaching -3 from the right side, what is happening. So how do we find that value? Remember, that's when we use algebra to simplify. So we can actually break this down into 3 different parts. Let's go ahead and look at the limit as x approaches -3 from the right for just the absolute value of x plus 3 over x plus 3, and then we can add that to the limit as x approaches -3 from the right for the square root of x plus 3, and then we have plus the limit as x approaches -3, again from the right for just 1. So this end part is the easiest part. We know the limit of a constant is a constant, so we know that's going to stay as plus 1. Here, if I plug in -3 into the square root function, -3 plus 3 would be 0, and the square root of 0 is 0, which is okay. So this right here gives me 0, so now we have 0. So we just need to figure out what this part is, because when I plug in -3, it makes my denominator 0. So remember we said when that happens, you want to see if there's some algebra you can do in order to eliminate that. If I'm looking at 3 from the right, that means I'm using the positive absolute value answer. And so the positive absolute value answer would just be x plus 3 over, and then down here we just have x plus 3. So we're looking at the limits as x approaches negative 3 from the right for this. And what's x plus 3 over x plus 3? Remember, that's just equal to 1 because you have the same thing, or divided the same thing. So really, this is equal to a limit of 1. So we'll just write it over here. So now you can see you have 1 plus 0 plus 1. So that means that this entire limit is equal to 2. So let's go ahead back to our graph to kind of confirm. So if I look at my graph right here, it even looks like on my graph I'm approaching that y value of 2. If I hit trace, you can even see right here that as we're approaching negative 3, it looks like we're approaching a y value of 2. We can use our table and put it on ask, and we can plug in, remember, very close values to the right of negative 3. So to the right of negative 3, again, if we have negative 2.9 and then negative 2.99, the more and more closer we get to that value of negative 3, notice that, say I didn't plug in negative 3, I put this value in, I would get closer and closer to 2. So that's a way that you can also confirm that you're approaching 2. But of course, we can't plug negative 3 in because it makes my denominator 0. You would get an error. So you're just plugging values very close. And even if I tried to do like we did in the last one, so in the last one it was from the left. So if I try to do from the left side, which would be negative 3.01, you'll notice that it's going to say error because we said that wasn't in the domain of the function. And if I look at this one algebraically over here, 3 from the left, if I would have done that algebraically, I would have had the negative answer for the absolute value. So this would have been negative x plus 3 over x plus 3 plus, and then right here I have the square root of x plus 3 and then plus the 1. So if I plug all the values in this case I would get, if I were to try to algebraically do this, if I thought it was in the domain, this would give me negative 1 plus 0 plus 1. So then you might think that your answer in this case would be 0, but again, that's why it's so important to check your graph and to check your domain, because we actually know that that is not part of our graph. So we can't say that we actually have an answer. So be very careful, because even though I can algebraically still work this out individually, I don't have it as a part of my domain. And so that concludes our one-side limits. And of course, I want you guys to, especially if you're going into calculus, you really need to be able to algebraically do this. If you're not really planning on going to calculus, then use your calculator to help you. You have it as a tool. It's real easy to kind of use the table that we learned about by using your table set, looking at the graph to see what your equation is going to be approaching.